Hello everyone, thanks for giving me the opportunity to speak. The problem I'm going to address today is how to define entanglement in a gauge theory. The reason this is confusing is Gauss law. So Gauss law relates the electric field entering a region to that leaving the region. Okay? And because of this, the degrees of freedom, the incoming electric field and the outgoing electric field are not independent, which means that the Hilbert space, the full Hilbert space, doesn't factor into an inside part and an outside part. So what do we do about this problem? Basically speaking, we ignore it. Instead of looking at the set of physical or gauge invariant states, which is the set of states that satisfy the Gauss law, we look at the extended Hilbert space, which has all states, whether or not they satisfy Gauss law. Okay? And because this extended Hilbert space doesn't know about the Gauss law, it does factorize into an inside part and an outside part. Therefore, that's a natural reduced density matrix. Therefore, there's a natural entanglement entropy. Our definition is just to use this entanglement entropy as the definition, as the entanglement entropy of your gauge invariant state. Okay? And this is possible because the gauge invariant Hilbert space is a part of the extended Hilbert space. There's a natural way to embed it. It has some nice properties. So in emergent gauge theories in condensed matter systems, which are theories where the gauge symmetry only appears at low energies, it's a natural definition because the extended Hilbert space is a natural Hilbert space. On the lattice is given by a replica trick using the standard Wilson path integral. This replica trick, you can take the continuum limit of it, and you get more or less the continuum replica trick. There's a small subtlety to do with gauge fixing on the boundary, where you get a second term. The second term is proportional to this mod G you see here, which is the number of points in the gauge group, which is not the volume, but the number of points. So it's infinity for a continuous Lie group like U1, SU2. It's a bit bothersome, but it's proportional to the area as well. So it doesn't contribute to non-universal quantities, so we are not very bothered by it. And because it gives a replica trick answer, we know it has to agree with Ryuta-Kanagi, again up to this term. Okay? Now we've ignored gauge invariance to define this entanglement, but it still plays a role. And it plays a role in the fact that the entanglement decomposes according to configurations of electric flux leaving the boundary. Okay, I'm going to call this K. Now for a U1 theory, K is your the normal component of your electric field, the one you're used to. For a SU2 theory, for example, you won't take the normal component of the full of the electric field itself, but the Casimir of it, like Jx squared plus Jy squared plus Jz squared, something like that. So you get three terms. One is this pk log pk term, which is in the middle, which comes back from the fact that measurements of this electric field on the inside and the outside are perfectly correlated. The first term, the pk trace rho k log rho k term, is the average of the entanglements in each k subsector. And the third term, which only turns up in non-abelian theories, and it turns up because to form a singlet from two spin J objects, you need a state like this, Jm tensor J minus m sum over m. So this is a fusion entanglement because you're summing over m. And this third term comes from there. Okay? And all these three terms have distinct information theoretic meanings. So the first term, the pk trace rho k log rho k term, is a distillable entanglement. This is the only part that's actually entanglement. It's the number of bell, in some precise sense, it's the number of bell pairs equivalent to your gauge theory state. The second term is classical correlation. It comes from the correlation of two gauge invariant operator outside and a gauge invariant operator inside. So it's real correlation, but it's not entanglement. Okay, as Bell explained to us. The third term isn't even classical correlation. It comes from the correlations of non-gauge invariant operators. Of course, in an emergent gauge theory, it's still real correlation. But anyway, it's something that looks very non-physical. This is really, this interpretation is the final result of my talk. You might be tempted to say, only the first term is real entanglement. I'm going to call that my entanglement entropy. However, as I told you earlier, all three terms contribute to the replica trick, to Ryuta-Kanagi, so the natural thing to do is take all three terms. Thank you.
Question? Okay. There is no.
So
can you think of this prescription as corresponding to some specific boundary condition for the gauge field inside your, or at the boundary of your region?
Boundary conditions for your replica trick path integral?
No, I mean for the original theory, can you consider it as coming from some specific boundary condition along the entangling surface?
I'm not sure, sorry. Okay, so what you can say is it's really integrating over all del dot A gauges. Del dot A equals alpha of x. You integrate over all of them. So it's some integration over boundary conditions. That's the best thing I can say. I don't know a very precise statement, I'm sorry.
One additional question.
So just as a follow-up to that, isn't it right that you can think of this as adding charges on the surface, on the entangling surface, and then, which is what allows you to relax the Gauss law, and then computing the entropy in this extended theory with these extended degrees of freedom? So
yes, in fact, the way condensed matter people like to think about it is exactly that. Just inside the boundary, you add charges, and just outside you add the opposite charges, and these are infinitely massive, so they don't have dynamics. So these two, the second and the third term are the entanglement of those infinitely massive charges.
Okay. Let us thank Ronak again.